Part B.1. First, we start a new part. Part B, cache mapping and cache structure. Actually, in this part, we have, other than these two topics, we have another important one. Memory access performance. Yeah, so that's the third topic. Very important. Yeah. All right, so let's start part B.1, direct mapped cache. Yeah. How to place a block in cache. The reason we use cache, we want to get a fast memory access performance. In order to do that, then the first thing you need to answer, you should find a faster way to place a cache block. So this time we have this concept. We put one block of data. One block of, so here, because that block could be data and instructions. So one block of, let's say, the general data, right? Instructions we can also treat as the general data, right? So we do not separate. So one block of data from main memory into the cache. There are many different ways. Which way is the best? Which way is the most efficient way? So we want to answer that question first. All right. When a block is loaded from main memory to, so this is a design question. When we answer this design question, we need to set our design goal. Okay. So look at design goal. First, easy to implement. We don't want to have some method that is very complicated. So you need to do a lot of things to find a location for this block. So that's not good. Second, good performance. The overall performance should be good. This performance, including fetching. Because later, you need to fetch that block and send it to CPU, okay? That part you also need to consider, okay? All right, so locate, fetching, right? All right. 3 algorithms. The first one, direct mapped cache. Next page, we talk about direct mapped cache. Second, fully associative cache. Third one, set associative cache. There are these 3 basic algorithms. All of them satisfy, first, satisfy the first, easy to implement. Easy to implement. But good performance, here I can tell you the answer. The first one, performance not good, performance not good. The last one, the performance is good. Is good. The reason we start with the first 2 relatively bad algorithms because we want to use that as the background for the third efficient algorithm. All right, so let's start with the first method, direct mapped cache. How to map a block in the location of a cache using a simple formula. The formula in this way, block address. First, you get a block address. This block address in main memory. Each block, when you fetch it from main memory, is there an address associated with it? Yes, there is an address associated with that block. Okay, so we take that block address. Now, then we mod operation. We do mod operation. Mod what number? The number of blocks in cache. A cache can hold certain number of blocks. So that number, we use it as the, divisor. So we mod that number. We mod that number and get the remainder. That remainder will be used. So this whole thing, that remainder will be used to give us the location of that block in cache. How about that? That method is simple, right? Very simple. Very, very simple. Yeah. But the problem, later we will see the performance. The performance is not good. Not good. Yeah. All right. So next, let's look at the properties of this method. Okay. So what is the properties of this method? First, each block in the main memory is mapped to only one location. Only one location in the cache. That's the main property of this method. Because after the modular operation, you can only get one possible answer. The remainder is unique. The remainder is unique. So that means in the whole cache, there is only one slot you can go. One slot, this particular block can be sent to. So that's the main property. This main property results in two other properties. One advantage, one disadvantage. Big advantage, even bigger disadvantage. Okay? Advantage, although it is good, but its impact is not that good. Okay? Its impact is not that big. Yeah. Disadvantage, impact is pretty big. Yeah. So that's why the overall performance is not good. Is not good. Yeah. Let's see the advantage first. Short hit time. Short hit time. Yeah. Later, when we need to find this block using its address, because we will have the address, we will use the original memory address to find the block. Okay? Yeah. Use the original address. When we say address, if we do not mention what address, we mean address in main memory, in memory. Okay? Yeah. Original address to find a block in cache. That's the way. Yeah. All right. Shortest hit time. Why? Because when you do this modular operation, you only get a one number. You just go to that slot to check if the data is there or not. That's fast. You only need to check once in cache. If fails, it's a cache miss. If you find it, it's a cache hit. Very fast. So this is an advantage. Yeah. But later you will see this advantage, the impact is not very big. It's good, but it can easily overshadowed by other negative factors. Yeah. All right, so next, disadvantage, high miss rate. What is the high miss rate? First, the miss rate concept, right? Yeah. In our part A, we learned this miss rate concept. So that is when you need to find required data in the cache, you couldn't find it, you get a miss. That percentage, you need to calculate the percentage, how big it is. That percentage, miss rate, you're related to the miss rate. Yeah. Here, this way, the miss rate is high. Yeah, why? So you can think about the scenario in this, like this. When you put a block into the cache, only one location you can put there, all right? When you put a new block in cache, the old block that occupy that slot is replaced by the new block. Old block replaced by new block. That means the old block data cannot be accessed from cache anymore. Okay? Cannot be accessed anymore. So the next time, if the CPU needs to use the data from an old block, it's a cache miss. It is a cache miss. Then the CPU needs to send a signal to main memory to load that old block another time. This will cause high miss rate. Yeah, because too many old blocks are kicked out of the cache, and too many blocks need to be reloaded from main memory into the cache. That will cause high miss rate. High miss rate. And this is a negative factor, and its impact is big. Very big. Much bigger than this one. The shortest head time, that impact is not that big. Not that big, So that's the main reason this whole method is not good. Whole method, not good. Not efficient. All right, so this is the first video, B.1. The second video, we will talk next two methods. All right, so let's stop here. Yeah.